Hello SGD, this will be a compilation of some older videos but piecing them together with some new pieces. So we'll be looking at hermeticism, measurements, measuring time, measuring angles, measuring length, and some very simple, very beautiful geometry, the Fibonacci and the Lucas numbers and the geometry of the spirals created by them, how we can use those to draw the three Giza pyramids, the Great Pyramid or Cheops, Caffrey Pyramid, and the Menkaura Pyramid and what comes from them, and analyze the connection to the golden number or phi, and how the Lucas and the Fibonacci series, as we see here, have a lovely set of connections. So by drawing these three pyramids, we're then going to go on and show how those essential simple geometries link all the other of the grand pyramids in Egypt, including the Red Pyramid, Bent Pyramid, Maidum Pyramid, and many others, but also link that to not just one but multiple sites in Thebes, just next to the Valley of the Kings, such as Temple of Luxor and the Temple of Karnak, Colossi of Memnon, and but also with archaeoastronomy as well. And so how this very simple Pythagorean geometry, the Fibonacci, the Lucas series will link many things. And so if you have a compass and straight edge, get them out. We'll do some drawing exercises and then go a little bit further. If you've got a spreadsheet, I'll show you how to use Microsoft Excel to examine these numbers, the Lucas and the Fibonacci numbers, and how they define the three Giza pyramids, but also meant essentially all of the other of the great pyramids. And that same math and geometry also embeds a whole series of beautiful connections which are written into the laws of geometry and math, and therefore other universal laws as well. So pause, go get your compass and straight edge. It's very simple drawing, and then we'll go further because it connects many things. It's sort of a synopsis of many other series I've did it, but again just based on very simple, very elegant arithmetic and geometry.
Okay, the Great Pyramids of, well, the three pyramids of Giza, and well, actually, we're just going to draw it from the vesica, and it's just this really simple, easy format. And from simplicity comes, well, Fibonacci numbers firstly. So we have the Fibonacci numbers and the Lucas numbers. Now both of them will lead us towards the golden ratio, but we also have the three pyramids famous at Giza. So we have the Menkaura Pyramid, which is 125 Egyptian royal cubits high and 200 wide, which is a 5:8 ratio. Then we have Khafre's Pyramid, which is 274 Egyptian royal cubits high, and at the base 411, which is a 2:3 ratio, and that's that one that still has the capstones at the top, often confused with the Great Pyramid. And then we have the Great Pyramid itself, which is 280 Royal Egyptian cubits high, and at the base 440, which is a 7:11 ratio. Fibonacci numbers, okay, the vesica Piscis, now that's a 2:3 ratio. One, two, three wide, 1, 2 high, 2:3, which is Caffre's, but Fibonacci numbers 1, 1, 2, 3, 5, 8, 13, but that's more than enough. Lucas numbers 1, 3, 4, 7, 11, 18. 7-11, that's proportions of the Great Pyramid. 7-11, also Maidum Pyramid. Now this 2:3 ratio, you also find it in these unfinished pyramids, which tend to have a base of 100 Egyptian royal cubits. But okay, so this is not just this actually defines so many of links other pyramids. So Great Pyramid, Maidum, these unfinished pyramids point towards this 2:3 ratio, vesica ratio, which is also Fibonacci ratio. Menkaura Pyramid 5 to 8, also a Fibonacci ratio, which again, all these will get closer and closer to the golden number. But you can draw those in and use it to draw a spiral. And missing a text somewhere, it's fallen, but anyway. Begin with a construction line. Because I want to fit it into camera, I'm going to start with a small vesica. Hopefully I'll get it all fit into camera. Okay, with that we now can draw a construction line, cut it down the middle, which gives us a 90, 90, 90, 90 degrees. Excellent template for all sorts of constructions. Keeping the compass setting without changing it. Mark the top. Mark the bottom because we want to create this 2 to 3 rectangle. Do that again on either side, draw an arc. Draw an arc again. And now we change the setting. Point on the middle to the, again using the vesica to give us these proportions. And what we've done now is created the points we need for this 2 to 3 rectangle. So now the rectangle enclosing the vesica 2 to 3 ratio. And now what I'm going to do is actually extend these lines out because this will help in the later construction. Because I'm using a thick point, okay, if you draw it properly, take your time, thin point, this will perfectly line up. And what we already have is the cross section of Khafre's Pyramid, which is a 2 to 3 ratio, which means it's a 2, 3, 4, 5 triangles, which is also defines the upper chamber in the Great Gallery, and again so many other of these smaller, lesser known pyramids as well. Okay, so that's a cross section of Khafre's Pyramid. It's a 3, 4, 5 triangle, 3, 4, 5 on the other side. But also before I go, so back to the Fibonacci numbers. So first we have Khafre's Pyramid, 2 to 3, 2 to 3, Fibonacci numbers, 2 to 3. And now I'm going to draw Menkaura Pyramid and create that, which is a 5 to 8 ratio. 5 to 8 Fibonacci numbers. Now you can do this with a spiral, the important Fibonacci spiral, or a Lucas spiral, but to begin with, which way will be best to work? To do these, what you need to do is to set the compass to the longest edge of the rectangle, which would be there. Okay, it's the first part of it's only a quarter circle, so the longest edge of a rectangle, a quarter circle, and it will create this. Now I also want to mark out that point, because what we have now is another larger rectangle which will grow closer and closer to the golden number. So original rectangle 3 to 2, now it's 3 to 5, 2 plus 3. And actually I'm going to extend that one out. Yep, I'm in camera. So now we have a 3 to 5 rectangle. Find the longest edge of that rectangle, set the compass to there. needed to extend this line out a little bit. And with the compass still set there, you can just also mark out this line, which will give us the next rectangle, which is a 5 to 8 rectangle. And we've started to create the spiral. And so now it's 2, 3 to 2, 3 to 5, now 5 to 8, 5 to 8. Well, of course, because it's going to grow by Fibonacci ratio, but also 5 to 8 is a proportion of Menkaure's pyramid. So what we have here are all the points you need to do that pyramid as well. So it's very clear. Now what I want to now find is the exact midpoint, and I'm going to do that just by bisecting the line. All you need to do is extend the compass to over halfway, just eyeball it. Draw an arc, do the same on the other side. That now cuts this line in half, and I only need to mark that portion, because now we have a 5 to 8 rectangle, which means that the triangle on the inside is going to be 8 wide to 5 high, and there we have the plan of Menkaure's pyramid. Now, of course, these are not in proportion, but you can just build up the proportions once you have the angles. Is the difficult part. You just increase or decrease units of measure. So now we have Menkaure's pyramid, which is 125 high by 200 wide, 5 to 8, 8 to 5. Khafre's pyramid, 2 to 3. And now we go back to Khafre's plan, or the original vesica, this 2 to 3 ratio. What you also have is, well, this rectangle here is 1 to 3. So we can to construct the integral, it's built into the proportions of it. So we have now a 1 to 3, which are the first two of the Lucas numbers, 1 and 3. And this is going to lead us to 1 to 3, 3 to 4, 4 to 7, 7 to 11. That's the ratio of the Great Pyramid, Meidum, and it's also built into so many other ancient structures. Now, which way will be the best to do it? And not for me to get outside of the paper. Again, you just, so 1 to 3, find the longest edge of that rectangle. Quarter circle. So 1 to 3. Now 1 plus 3, so it's a 3 to 4, and I can mark out that line to get this rectangle. And actually I should extend that line out. Okay, 1 to 3, 3 to 4. Now find the longest edge. And we just extend another quarter circle. So that's the point there. Same. 1 to 3, 3 to 4, 4 to 7. And now that will actually be will be our point there. And now, Oop, I hope I didn't mess this up and I'm outside of the paper. Nope, I'm in. And I'll extend this line out. Should have extended this line down originally. We're still on that setting there. And so I can just go across, mark, and now I have a 7 to 11 rectangle. Seven to 11, then a 7 to 4, then a 3 to 4, then a 3 to 1. So now we have exactly the same thing what we need to do the Great Pyramid. 7 to 11 Fibonacci numbers, and 11 over 7 is very close approximate of pi over 2. Now what we need to do is find, this is the longest line, so we need to find the halfway. We do that by extending, we're just going to bisect the line. As long as it's over halfway, you draw an arc. Do the same on the other side. You don't need to draw a whole construction line, we just need that point, and that point. And there we have, although it's tilted on its side, we have the Great Pyramid, 7 to 11. Fibonacci, Lucas, from the vesica, gives us the pyramids, and not only the three, because well, there are other ones connecting, and the Menkaura, Caffre's Great Pyramid. That would be the Great Pyramid there. Caffrey's Pyramid here. Menkaura's Pyramid here. Once you got the proportions, it's just a matter of counting out the units. But what we have is, we begin with a vesica, and then we grow a spiral from the same vesica to the 3 to 1, grow a spiral, and what you have are pyramid plan. Circles and lines, compass and straight edge, and bang.
So by beginning with the vesica piscis or vesica piscis, we're able to create a Fibonacci spiral and a Lucas spiral, and thus we've been able to draw the three famous Giza pyramids. Fibonacci numbers, Lucas numbers, but let's go look a little bit further. So Lucas Fibonacci spiral, they begin differently, but they'll very quickly come to the same point, and that has to do with the golden number. Now the name Fibonacci comes from Leonardo Fibonacci. He popularized the base 10 Hindu-Arabic numbers. If you take Fibonacci numbers and divide them by the previous, so 1 divided by 1, 2 divided by 1, very quickly they'll start coming to the golden number, or phi. 1.61803398887. The further you go, the closer and closer you'll get. And the same thing happens with the Lucas numbers as well, but we'll examine those because there's a lovely series of connections also between the golden number, the Lucas and the Fibonacci numbers, but there's also some demystification to be done, but in that itself will lead to some other really nice connections geometrically. So Fibonacci will also bring in the Lucas numbers, but how it links all of the pyramids essentially. So we begin with the Fibonacci numbers 2 and 3. So just like the vesica piscis, one circle with the center, second circle has a center on the edge of the first. They're both the same size. It creates a 2 to 3 ratio, and that gives us the Caffrey Pyramid. If it's 3 wide, then it's 2 high. These are Fibonacci numbers. Now we can start linking other pyramids because, for instance, the Caffrey 2 to 3 ratio of the vesica piscis also defines the height of the Great Pyramid in relation to the base length of the Red Pyramid. So we can now use that to link other pyramids. So I've just put the Great Pyramid in its position there, and we're linking the Red Pyramid base to the Great Pyramid height via Khafre Pyramid, 2 to 3. Now we have the Lucas numbers. 1, 3, 4, 7, 11, 18, 29. Now a nice link with the Lucas numbers is that if you take every second Fibonacci, 1 and 2, add them together, you get 3. Next one down, 1 and 3, you get 4. 2 and 5, you get 7. And that carries on. That's just one of the lovely links with the Lucas numbers. And in the second half, we'll do some spreadsheets and look at the connections between phi, Lucas numbers, square root of 5, and these unique series of relationships, which also defines many of the pyramids. Now, Lucas numbers 7 and 11. The Great Pyramid, 440 Egyptian cubits wide by 280 Egyptian cubits high. That gives us a ratio. So that if the base is 11, then the height is 7. 7, 11. Now, that's the same as the Meidum Pyramid. The casing stones are still there, so we're able to work out the angle. It has the same angle, and because of the base still being there, we can work out the original height. So 275 Egyptian royal cubits base length, 175 Egyptian royal cubits high, which also is 11 wide to 7 high ratio, just like the Great Pyramid. Now what's interesting is that the ratio of the Meidum Pyramid and Great Pyramid having the same proportions, what's the relationship of their size? And so we can just take the base of Meidum, 275, divided by the base of the Great Pyramid, or you can do it by height. 175 divided by 280 gives us 1.6. That's a ratio of 5 to 8. If the Great Pyramid is 8 high or 8 wide, then the Meidum Pyramid is 5 high or 5 wide. And relationships between these based on the same very simple geometry, but that's not all, of course. Let's look at the Menkaura Pyramid, because the Menkaura Pyramid, east and west side are a little bit shorter, but the south and the north side are 200 Egyptian royal cubits base length with a height of 125 Egyptian royal cubits. That gives us a ratio of 8 wide to 5 high, the same relationship that defines the Meidum and the Great Pyramid. Now, I've already mentioned that the Red Pyramid and the Great Pyramid are joined by the 2 to 3 ratio of the Caffrey Pyramid. Well, the Menkaura Pyramid has another series of links, because the Red Pyramid, and the Bent Pyramid, they're both 200 Egyptian royal cubits high, which is equal to the base length north-south of the Menkaura Pyramid. But in terms of height, if the Bent Pyramid at 200 is 8, then the height of the Menkaura Pyramid is 5. The height of the Red Pyramid, 200, therefore it is also at a 5 to 8 ratio in regards to height of the Menkaura Pyramid. And let's just skip back to the 2 to 3 ratio of the Caffrey Pyramid and how it relates to the Great Pyramid proportion in regard to the Red Pyramid. Well, Caffrey is very cool because, so just taking a screen and we'll zoom in more. So here we have the Giza Plateau, and we have the Caffrey Pyramid, which is 2 to 3, 3 wide, 2 high. Therefore, the right angle triangle is a 3, 4, 5 triangle, the first of the Pythagorean triplets, and those are the angles of a 3, 4, 5 triangle. Now we have all these, now the Red and Bent Pyramid and the Meidum Pyramid a little bit further south, but we have these other of the Grand Pyramids. Pepi the First, 150 Egyptian royal cubits wide by 100 high. Again, casing stone survive, so we know the angles, even though there's been loss at the top. That is a 3 wide by 2 high, just like the Khafre Pyramid. Same with Merenenre, Pepi the First, Teti, Yusakaf, Neferakare, and the Amenika Mountain. Now that's in a really bad state, that one, so I'm going to put an asterisk next to it, but based on what's surviving, all the work done there would point to it also being the same. So Caffrey Pyramid, which gives us links to the Great and the Red Pyramid. Also, that geometry can be found in these other pyramids too. Now, it just so happens that the Pyramid of Kukulkan, the steps are at 45 degrees, but like the stairway, but these stepped terraces have the same angle of the Khafre Pyramid. And the equinox relationship between the two is interesting. But these are pyramids. This can also be applied to many other connections down in Abydos and Thebes, for example. Now you have to think also of the flood, because the flood will be an important link in there as well. There were 3 seasons in Egypt. The Akhet, or the flood season, was began with Egyptian New Year on the summer solstice. So there we have the Giza Plateau. Now we have the Caffrey Causeway, which goes down to the door to the Caffrey Valley Temple. But the alignments in regards to winter solstice, equinox, and summer solstice marks the beginning of the new year, and viewed from that position, which is also marked out by the Caffrey Causeway, the sun will set exactly in between the Khufu and the Khafre Pyramid. Now also then I went on, anyway, these links, now that angle, I'll show again later. Just a correction, and I'll clear it up a bit later when I'll insert the image into the picture there. But the causeway which comes off the Great Pyramid is also 14 degrees, but it's 14 degrees above from true east, so it points to the midpoint between the summer solstice sunrise and the equinox. And original narration, I just did a boo-boo there and said it points to the summer solstice sunrise. That's not the case, it's halfway between, but it has that same 14 degree angle as the Caffrey Pyramid, just reversed. But so that doorway where the 0 point is, I did in this in another video, from that, if you take measurements from this doorway where the Caffrey Pyramid Causeway hits the Caffrey Valley Temple, the measurements, the equidistant, and well, just a whole series of things. But that's what we come back to is at this point is well, in terms of a measurement, but these angles and where they, each one of these has great significance. For instance, the winter solstice viewed from there touches the corner of the Menkaure's tomb pyramid, marking the winter solstice, and these other features too, but measuring time, measuring length, measuring angles and geometry as well. So you have all 3 seasons in Egypt on the viewed from the 0 point where the Caffrey Causeway hits the Caffrey Valley Temple. The sun will set directly between the Great and Caffrey Pyramid. That's summer solstice. That marks the beginning of the Akhet, or flood or inundation season. 3 seasons per year instead of the 4. And the symbol for that is Akhet, where again you can see the sun between the 2 mountains as well. The horizon is another word for it. Doesn't happen anymore because of the High Aswan Dam, but the flood season firstly would come right up to the base of the pyramids and the Caffrey Valley Temple. It was the heartbeat of ancient Egypt. Now the angle between summer solstice and winter solstice is 56, or 14 times 4, which is marked out, for instance, in these causeways. So that's 180 days there and 180 days back, but there are 365 days per year. Well, on the solstice, winter and summer, for a 2 to 3 day period, the sun appears to rise and set in the same place, and that's the intercalary period. Again, Akhet lasts for 120 days. 120 days is just off the base number, 37.33, but if you include exactly what point in the solstice do you begin counting, the beginning, the middle, or the end, again there's a 2 to 3 day period. So better would be with the summer solstice, so you'd get 37 degrees because you have that 2 to 3 day period. And Khafre Pyramid, 3 wide by 2 high, 411 divided by 3 is 137, 274 divided by 2 is 137. There's a nice link there as well. But this summer solstice is also important because we'll look at Thebes, but the Osirieon, where we have the flower of lives marked in there, and that's just a whole series of vesicas. That's all it is. So you see how it's just a vesica. This is used in architecture and symbolism across time, across cultures, across the world. We did that drawing again, but it's all comes from the vesica and the 2 to 3 ratio of Khafre's pyramid. Alright, so that 120 day period of beginning Akhet, summer solstice, the angle would be fraction either way of 37 degrees, again depending slightly. Now that here comes the angles of the 3, 4, 5 triangle, 36.869, which you could just 36.87, which is it's essentially it's that angle 36.87. You can filling that fraction of an angle is fiddling a few hours. At what point do you define the key point in the solstice where the sun appears to rise and set in the same place for a 2 to 3 day period? 360 days, 3 months, 3 seasons of 120 days times 3 is 360, plus you have 2 to 3 days of solstice summer, 2 to 3 days of winter solstice, and there's your 365 day calendar. And again, also have a 3, 4, 5 triangle in there. So again, these inherent angles, not just the lovely geometry of a Pythagorean 3, 4, 5 triangle, but also the seasons and the flood. So there's just that's the doorway to Caffrey Valley Temple leading up the causeway, and it's a 0 marker because just the measurements and the definitions from there are just spot on. Back down to the Osirieon at Abydos and how the pyramids have the angle as a pyramid, but on the floor plans we have the same angles of the Khafre Pyramid. And we go, even the construction style of Khafre Valley Temple and Osirieon is this very barbaric sort of stuff, primitive style if you want to say, without decorations and that type of thing. And let's look further at the geometry and the links between the pyramids, these angles, and the timekeeping as well. Also worth noting, from the 0 point here, we see the corner angle of the pyramid, not the slope angle. We see the pyramid from the corner, and we have the corner angle. We see the Khafre Pyramid in profile, and that's an very important feature too. Okay, from this very specific point, you get lovely connections in measurement and distance between all of these pyramids, including Menkaure's. But again, important note is that what you see of the Great Pyramid is you see the corner of it, not the profile. So you're looking essentially directly at Khafre's pyramid, but the Great Pyramid is seen from the corner. So what you're really getting, you're not observing the 51.84 degree angle, you're seeing the corner angles, which are 42 and 48. Give or take hundredths of a degree. Each side varies slightly, but that's the angle that you're seeing there, 42 or 48, in other words 96 across the top there. So these all being very important to Akhet, even the symbolism of Akhet with the sun coming down between the two mountains on the summer solstice, the beginning of the season of Akhet. So Caffrey Pyramid in profile and Great Pyramid from the corner, and those angles are key features. So again, the flood all across Egypt. Even the symbol for New Year's Day is Akhet, but it has a palm frond at the top and that represents time. Okay, now summer solstice, so we go from Giza Plateau and we go down to Thebes, where the Valley of the Kings is, Luxor and Karnak and other major temples. Again, the flood is so important. There's an aerial view. There's the colossi of Memnon, and that's what it used to be like in the flood season, where the water would come way up. So just to Photoshop that in, we see where the water level would go to before the dam changed things. And even Luxor and Karnak had great walls built around them, protecting them from the flood. So from where the river is now, we're looking about 4 kilometers. It stretches further in, which means that at places like Karnak and Luxor, where they move these giant obelisks, places like the Colossi of Memnon, which have other statues behind it as well, you quarry your stone, take it a very short distance to the river. If you quarry it close enough to the river, you just wait for the river to rise, and then you float it down the river, and you don't need to drag it across land. The water does the work for you. Think smart, not hard. So just like the walls that are around Karnak and many other temple sites as well, the flood was all, it's the spine of Egypt, and the flood is the heartbeat. That's what gave them their agriculture. But here around Thebes, Luxor, Karnak, the Colossi, Menet Habu, Deir el-Medina and Deir el-Barahi. So first Karnak Temple. Just like with that alignment in the Giza Plateau, 28 degrees, therefore you look down the center, and on the summer solstice, sunset, or the winter solstice, sunrise in the opposite direction, that's the alignment of the temple. So just like that 28 degrees we find in the Giza Plateau. Again, you can see where the waters rose, because by that time, 1890, the walls had long been had not been repaired. Okay, so Karnak, 28 degrees, and not only that, it points to the Valley of the Kings. Here we see Deir el-Barahi, Valley of the Kings. It too is angled 28 degrees, same solstice alignment. Colossi of Memnon, 28 degrees. Now we have that, now think of the pyramid, Great Pyramid, corner angle 42 and 48 degrees. Go down to Luxor Temple, Thoth and Sheshet there, of course. Now let's see alignment there. Now there is a little kink, but the main alignment of the temple is 36.87 degrees, which is the 120 days of Akhet, and well, it's the Khafre Pyramid at 2 to 3 vesica ratio, which gives you a 3-4-5 triangle. Again, the 120 day period between summer solstice and the end of the season of the flood. This changed angle points directly to the Temple of Karnak. So we follow that, and again pointing directly to, and at a nice, pretty much there in the center, will probably be a significant spot. Along the way we have an avenue of Sphinxes. The avenue of Sphinxes there. Okay, but there's another thing, because along the route there is this kink. So the road carries through, but you can see that the avenue of Sphinxes has this dog leg in it. And what's the angle of that? 28 degrees again, just like the Giza Plateau. So 28, 28, 28. And of course the Khafre Pyramid angle in there, which is also related to the 120 days. Menet Habu, another major temple, included well, many features, but what's the main alignment? Now it points to, now if you go back to these ones, points to the Valley of the Queens, points to the Valley of the Kings. Now this one points to the Valley of the Queens. I wouldn't be surprised if it points to a specific place in there as well. So you notice even it's off, again, that's pointing to the Valley of the Queens. Then we have this courtyard on the outside, which is again off axis of the major temple. What's the angle? 53.13 degrees, which is the Khafre Pyramid angle. Okay, now, and of course the main wall of the temple, 318 degrees, or in other words 42 off axis, and again this wall not lined up, it's a few degrees off. How many? It's 6 degrees, I forgot. Okay, well that's 48 degrees, so 48 and 42, 42 and 48 degrees from the corner angle of the Great Pyramid, and of course the 345 angle of the Caffrey Pyramid, and pointing to the Valley of the Queens as well. Deir el-Medina, now it was again, that's a line pointing to the Valley of the Kings. That was a very special site. It was segregated. It was where the craftsmen worked. They had very high privileges. They'll give them special privilege, where all the craftsmen worked. So the people working on the Valley of the Kings, who had to keep those secrets, they had really high special privileges. But what's the angle? Khafre Pyramid angle. So we're seeing these angles observed there at Giza, matching Akhet, the symbolism, but of course even the time, in the literal sense, symbolic sense, it's all there. It's all got to do with the flood. Now, that was Thebes. What about Abydos? We mentioned that, where we have the Temple of Seti and the Osirieon, which has the flower of life carved there into it. About the only decoration in that main body of the temple. There are other attached things with paintings and stuff, but that's the only decoration there. And what's the angle? 36.87, following through. And again, that angle reflects the 120 days of the flood, or the Khafre Pyramid as well. So yeah, that's the many archaeoastronomy, timekeeping, alignments as well. Now, I'll try to remember to go back and correct it, because again we have, for instance, the Caffrey Causeway is 14 degrees off east-west, and that's the same 14 degrees, that will touch the corner of Menkaure's, and just again the midpoints between the equinox, east-west, and the winter solstice or the summer solstice. Now that causeway which comes off the Great Pyramid, that's 14 degrees. That would point to that's a midway point. I said earlier that it's aligned to the winter solstice sunrise. No, sorry, correct that. I'll go back in the video hopefully and do it if I remember. It is the halfway point between equinox and solstice. 0 point. Okay, we come back to the start. So there are, with these angles of the Fibonacci and the Lucas numbers, which give the proportions, the basic proportions of a Great Pyramid, Khafre and Menkaura, which give you also the proportions of red and bent pyramid, and as well all of it, like Neferefre and all those other ones down south as well. So with these Lucas Fibonacci geometry that we drew, it's not just about drawing the 3 Giza pyramids, it's also about drawing other pyramids, and also those same inherent proportions give us the ratio of size between essentially all of the great pyramids, including the lesser known ones down towards Abu Sir and so on. And incidentally, they all point to Heliopolis too, just like the Giza pyramids as well. So yeah, that's from this geometry, you're not just drawing 3 pyramids, you're drawing a hell of a lot more, including incorporating the flood cycle, which was again the heartbeat of Egyptian life. And so all these other pyramids are Pepi II, Pepi I, Merenenre, Teti I, Userkaf, and Neferkare, all have that same angle. Of course, is Pyramid of Kukulkan, again Abydos and Thebes. So that's what you get from the drawing. Now it's worth. Now let's do another piece, and So the 7-11 proportion of the Great Pyramid and Meidum Pyramid, well, that's 7 to 11. Well, there's another link, and I come up with a way, maybe the best, as far as I could find. Archaeo, I always miss the A, and should be Arc, A-E-O-A. But the Menkaura Pyramid, which is 8 wide to 5 high, which also gives you proportions to the red and bent pyramid, has another neat little geometric trick in it. And as far as I know, with compass and straight edge, it gives you the most accurate way to draw a nonagon, and the proportions of the interior and the exterior angle of a nonagon are 7 to 11, just like the Great Pyramid. So I'll put that piece in there as well, and then we'll go back to the Fibonacci and Lucas numbers and look at the golden ratio and some really cool links between Lucas and Fibonacci numbers, especially in relation to the golden number and its relationship to the square root of 5. But Menkaura Pyramid, 5 to 8, and let's draw a nonagon.
Hello, we'll have a look at, well, Fibonacci numbers, how they relate to the 3 Great Pyramids at Giza, and also how they will bring us to the nonagon, or the 9-sided shape, or the 9-pointed star, which is technically impossible to draw perfectly with compass and straight edge, but we can do a very, very close approximate. I stumbled upon this looking into the pyramids, and I think this is actually the most accurate compass and straight edge nonagon that is known out there. I don't think it's been published anywhere else. I tried to find it, I couldn't see it. Perhaps it could have been, but either way, this brings us very nice knowledge connections to all 3 of the Great Pyramids, Fibonacci numbers, which of course relate to the golden section, just the inherent geometry of things, and again, phi ratios, as they are so wonderful. I'm going to begin with the construction line, and it all should work together. So if I probably should have room, but for instance, this is part of I'll insert a graphic here, but we have the 3 pyramids at Giza, the Menkaura, Caffrey, and the Great Pyramid. Now, these first 2, the Menkaura and Caffrey Pyramid, the basic plan emerges from this Fibonacci spiral, and then we'll go to the nonagon, and that gives us the ratio for the Great Pyramid. And so I have room, make sure I'm in camera. Okay, I've done a construction line. I'm going to be using 2 compasses because one I want to adjust, and I want to keep this one at the original setting. So begin with a vesica, 2 circles, the center of the second on the edge of the first. Now we have, from our construction line, now we can cut down there and create 4 90-degree angles. Place my point, and so that will just be a construction line, but now place the point at the center. Now the vesica piscis is 1, 2, 3 wide and 1, 2 high. So we already have a 3 to 2 ratio, and that already gives us the basic design for the Caffrey Pyramid, the second of the 3 Giza pyramids. So compass in the center. Now on the edge of a circle, I'm going to do the same. I'm going to draw a small arc and draw an arc again. You want it directly above. Do the same on the other side. What we're doing is we're going to draw a rectangle around this vesica. And with that, now I put my compass point at the center, find the edge of the circle. So now I go to the top, there in the center, mark again on the other side, and do the same at the bottom. Now we have the 4 points of the corners for the rectangle, 2 to 3 ratio rectangle, which encloses the vesica 2 to 3. And actually this line I'm going to carry on up to the top, markers going. Do the same with this line, and I'm going to carry it on up further. Oh, it's a little bit, okay, I'm just brushing, but if you take your time, use the finest point that you can, but with the numbers we can demonstrate the accuracy of the nonagon anyway. And again, I'm going to carry that line out. Let me get rid of this marker. And I'm carrying these lines on because they're going to be helpful in the construction of the Fibonacci spiral. Okay, so we have a 2 to 3 rectangle, 3 wide by 2 high. Let me change colours. And we already have the Khafre Pyramid, that central pyramid that still has its capstones on the top. So there already is your Caffrey Pyramid, which is 411 cubits, Egyptian royal cubits wide, and 274 Egyptian royal cubits high, 2 to 3 ratio. And from the vesica we have the Caffrey Pyramid. Okay, I mean, now I'm leaving this is still at the original setting because now I want to use this to help with the Fibonacci spiral. So I'm going to mark each one of those sides. And so since the Fibonacci is 3 wide, now I have 1 by 2. So what I have here is a square, and I have a 1 by 2 rectangle. I'm also going to draw a line here. So now I have one square, a second square, and a third square, which each of these squares is 1 by 1. This is a 2 by 1 square. Okay, so because we already have this circle, let me change the colour, because now we'll be drawing the Fibonacci. What colour would stick out better? Hopefully green. Just make sure my point of the marker is right. Okay, so I draw. Now we have a quarter circle. Now the rest of the Fibonacci spiral is just a series of creating squares and quarter circles. So that's our first quarter circle. Now I don't need to, and Fibonacci numbers, 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 13 would be the next, but we only need here because we're working towards a 5 by 8 rectangle. So we have a 1 by 1 square, 1 by 1. Every time you want to extend the Fibonacci spiral, you find the longest edge of this point, it's a square, so they're all the same, and then you extend it by a quarter circle. Let me get that accurate. So again, I've just used another quarter circle, and these are already the lines in the circles inherent in the vesica. So we have a 1 by 1, now we have a 1 by 2 rectangle, 1 by 2, and now we need to make a 2 by 3, and so where I ended the last spiral, now I adjust my compass to that point, and accurate with that. But it's just another quarter circle. And you can already see the snail spiral, the vesica spiral emerging. Well, I'm not sure if my compass will extend that wide, but so now we have 1 by 1, 1 by 2, and now a 2 by 3, which is the Khafre Pyramid. And now the longest edge of this rectangle is this. So now we just draw another quarter circle. And that's why I left these extension lines out to help with that construction. Okay, so now it's just another quarter circle. And if you're drawing it properly, you would also use that to mark. So now we have another square, but it's not necessary for where I'm going. And now my compass won't open that large. I should have, I guess it will, but it's just inside. Okay, so quarter circle, we extend it on the longer side. Now the longer side of this rectangle is here. Okay, so now another quarter circle. And so now we have 1 by 1, 2 by 1, 3 by 2, 3 by 5, and now a 5 by 8. And now I draw the enclosing rectangle around there. So just hand that line out. But now what you have is a 5 by 8 rectangle. Caffrey Pyramid is a 2 by 3 ratio, 3 wide by 2 high. Menkaura, the smallest pyramid, 200 Egyptian raw cubits wide on the south and north base, and it's 125 high, which gives it a 5 high by 8 wide. And well, now I just need to, what I want to do is now draw the the Menkaura Pyramid, so I need to find the center point so we can just bisect that line. Actually, I'll do it on this line. You should bisect it top and probably bottom if you're doing it, you know, just to be super accurate. But just extend the compass anywhere over halfway. Okay, actually, sorry, I should do it over here. You can just eyeball it to get halfway. And if I go to the opposite side, now I've bisected that line. So this would be exactly halfway between here and here. I could just mark that point. Now from the corner to there. And that gives us the profile of the smallest of the three of the Menkaura Pyramid. 200 Egyptian raw cubits wide, 125 high. Caffrey Pyramid, 411 by 274 high. Now, of course, they're not in scale, but Fibonacci numbers 1, 1, 2, 3, 5, 8. Is that now we've created a 5 by 8. Probably do it a little bit larger, but we have the three. I'll put an illustration here, but we have the three Giza pyramids: Menkaura, Caffrey, and Khufu, or the Great Pyramid. The Menkaura, the smallest of the three, is 125 Egyptian raw cubits high, 200 Egyptian raw cubits wide. That's this triangle here. That's the smallest of the three, the Menkaura Pyramid, which is a 8 wide by 5 high. The Khafre Pyramid, the one that appears to be the biggest, but it's on a raised platform. It still has the casing stones at the top. That's 411 Egyptian royal cubits wide at the base, 274 high. So it's 2 high by 3 wide, these Fibonacci. So that would be the profile of the Khafre Pyramid. That's the profile of the Menkaura Pyramid. We get these from the Fibonacci numbers. But then we have the Great Pyramid, which is 280 Egyptian royal cubits, 280 Egyptian royal cubits high, 440 wide. That's so 7 high by 11 wide. These are Lucas numbers, by the way. So you have Lucas 1, 3, 4, 7, and 11. I'll put a link in the description how the Fibonacci spiral and the Lucas spiral bring you to the same golden number eventually. But this 5 high by 8 wide, the Menkaura Pyramid, the rectangle here, so what I've done is I've just drawn a 5 by 8 rectangle, and we're going to draw the nonagon. We're going to create a nonagon that is toot my own horn, but seems to be the most accurate nonagon using purely compass and straight edge methods. And we get that, so this rectangle is this 10 centimeters high by 16 centimeters wide, therefore 5 by 8, just like this Fibonacci spiral we've got here, which is a Menkaura Pyramid. And so the Menkaura Pyramid would be the triangle in here, and then I've just simply drawn a circle centered on this corner. So now if I draw a line that's a diagonal, and I want to use again, if you're drawing this, you want to use the finest point as what's possible to get this as accurate as you can. But if we draw a diagonal through there, I'll put a card here. You can use trig, double check it, online right angle triangle calculator. We have a right angle triangle here. Let's call this angle A. Angle A would be 32.0053832 degrees. So the 5 by 8 rectangle created by Menkaura Pyramid is 32.00583, etc. Now we can just use the laws of Euclidean geometry, and now I'm going to bisect this angle, so I'm going to cut it in half. This you can do with 100% perfection using the Euclidean geometry. So I'm just going to draw an arc, and then I'm going to use this one. Now I just need to set the compass anywhere over halfway, and draw an arc. Do the same at the top, and now we've bisected that angle. There's my final point. Now a problem with drawing such as this is that the thickness of the pan and just human inaccuracies to get it perfect, but mathematically speaking we're going to use that. So if you do draw it, you can test it on GeoGebra or such programs to be sure. So now we bisect that angle, and therefore angle B should be, by strict definition, 16.0026916 degrees. And now I'm going to bisect that angle one more time. Now, technically speaking, the nonagon is impossible to draw perfect with compass and straight edge. But again, it's going to as far as I know, it's the most accurate one, and I got inspired to find this by, again, studying the pyramids in ancient architecture. Now this would also relate to the dodecahedron, so 32 degrees. I have a dodecahedron here. Now, if we lined it up so we have the axis of going across the middle, so it's perfectly lined up, if I rotate this 32 degrees, I should get the axis going right through the middle of this. So there's an application to the dodecahedron. Also the Sphinx, there are various analysis of the Sphinx face, and they've noticed a 32 degree angle in the face of the Sphinx, but I'm not too sure about that. But anyway, so we've bisected angle A, and now we've bisected angle, so we get angle C. By strict definition, if we draw it perfectly, at 8.001345 degrees. Now I can take, now I'm going to use the circle, because now we have all the points we need, because a nonagon is 9-sided shape, a 9-pointed star. 360 degrees divided by 9 equals 40 degrees, and if I add 32 plus 8, I would get 40.006729 degrees. So less than 7/1000ths of a degree, and that is with compass and straight edge, with the most steady hand, the most finest point. If you can, you know, like that's 7/1000ths of a degree is way beyond what a non-superhuman could achieve in this level. So, that would be, if I add 32.055 plus 8.001 degrees, I want to get 40 degrees to be a perfect nonagon. Using this construction, I'll get 40.0067, which is 7/1000ths of a degree. Again, essentially impossible for a mere mortal to achieve this level of perfection, no matter how fine your point is, no matter how much time you take to get this accuracy. But so angle C plus angle A will give us 40.006729 degrees. And so put my compass point on there. I adjust it to get as close as I can. And the problem with this compass and straight edge drawing is that any minor error gets grows every time you add to the construction, and again, to get within 7/1000ths of a degree is, well, again, very, very hard. Now, the shadow is confusing me a bit. Yeah, that should be. I want to get my point there. Okay, no, that's why the shadow of the point is. Okay. Give me a moment. I'm going to try to get this as. That should be it. Oh, no, it's still a bit big. That should be it. Okay, so if drawn properly, this angle D would be 40.0067 degrees. Now I can set my compass there, and Okay, now we can just chase that circle around. My hand out of the... There you go. It's even would be closer. Properly speaking, again, the thickness of a pencil, shaking hand, even the vibrations of traffic is going to affect you if you're trying to get within 7/1000th of a degree. So now we have 1, 2, 3, 4, 5, 6, 7, 8. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. We've created a nonagon, and that final angle, so if we had a perfect nonagon, that all the way around would be 320 degrees. Again, it's actually 320.0538332 degrees, so it's less than, the final angle chasing it out would be less than 6/100ths of a degree. You've drawn a perfect nonagon using the compass and straight edge method. Technically not mathematically super accurate, but again, in the human real world, if you can get anywhere close to that angle in engineering, you're going to be a rock star. So now I've just used a protractor to draw these out, because there's another aspect here in regards to the nonagon. Now I'll just draw them freehand, but let's say you want to you draw a hexagram, or as what most people would recognise, a Star of David. That's two equilateral triangles overlapping. You have to draw two triangles to do it. There is a way to do it with one line, but it doesn't create a regular shape. However, that's 6 points, so it's an even number. However, if you draw a pentagram, for instance, which is 5 points, you can do that in one line. So the nonagon, I've just marked out the points. It follows that rule because it's 9 being an odd number. So if I just follow this around, and so again we've won, without ever having to remove the pencil or the marker, you can create this 9-pointed star. Let's move it. Okay, so like the pentagram, you can do it with 1 point, but the interesting thing about the nonagon, well, you can also create a series of overlapping equilateral triangles, and I'll put an image of Kershaw here to show you what I mean. So if I start at 1 point and I skip 1, 2, and then I go to the third, skip 1, 2, go to the third, and then come back. Now we have an equilateral triangle. If I repeat the same again, let's get 1, 2, and this over here. So now we have another equilateral triangle, and then with the 3 remaining, we have a third equilateral triangle. So it's nice that this nonagon sort of is works in both worlds, both the odd and the evens in regards to making the stars from there. So we have two variations. So this is the one, for instance, used in the illustration by Kircher, which has the 3-4 triangles and the 6/5 ratio hidden in plain sight, so to speak. But now we can do a nonagon, so a 9-sided, and we just go from point to point. But that's where this, some interesting connections come in. Because now we have the center point, so the defining angle of a nonagon is 360 divided by 9, so that's 40 degrees. But we also have the interior corner angle, that's 140 degrees. Therefore the exterior corner angle is 220 degrees. Now the common divisor between them is 20, so in other words 140 divided by 20 is 7, 220 divided by 20 is 11, and that is the ratio of the Great Pyramid, which is 280 Egyptian royal cubits high and 440 Egyptian royal cubits wide, which gives us the pi and phi ratios in there as well. So that's a nice link. So from the Khafre and Menkaura Pyramid via the Fibonacci Spiral, we can create a nonagon which is so, its accuracy is above what's achievable with compass and straight edge. And the nonagon leaves us this important esoteric symbol, both this but also the crossover between the 5 and the 6 type of pattern, where it's one line or overlapping regular polygons such as a equilateral triangle. And then of course then we have these. Now here's another interesting feature, is so 360 degrees, each degree is broken down into 60 minutes, and each minute is broken down into 60 seconds. Now we use decimal, but the old school way was minutes and seconds, exactly the same on the clock, where 1 hour is 60 minutes and each minute is 60 seconds. Same principle in old school navigation. So 40 degrees is equal to 2,400 minutes on the compass, or 144,000 seconds. So that's one of these key ancient numbers, east to west, modern and old, 144, especially 144,000. I'll put some cards up about that. Now 140 degrees equals 13,200 minutes. Now that's half of that is 66, half of that again would be 33, but it's also equal to 504,000 seconds. Now 504 is nice, but okay, I'll put up something now about 5,040. And 220 degrees is equal to what's that, 1,200. Did I do that right? Sorry. Ah, no, forget what that. I've lost my mind. That's not 1320, that's 8,400 minutes of a compass, and this one is 13,200 minutes, or 792,000 seconds of the compass. Now each one of these is super cool. Now I'll put up some cards and images now. 5,000, sorry, yeah, 5,040. And all that's related to 792. And of course the Great Pyramid ratio, and also the Khafre and Menkaura Pyramid ratio by the Fibonacci. I'll also link in the video in the description how I use this same, beginning with the vesica piscis here, how I also get to the 7-11 ratio via the Lucas numbers. And by drawing a Lucas spiral, we also get the Great Pyramid 7-11 ratio. So the nonagon from the Fibonacci, and again, as far as I know, as I could find, this is the most accurate way with just compass and straight edge, and so accurate that it goes beyond the limitations of using tools such as these. But mathematically, geometrically speaking, it is not perfect. It is 7/1000ths of a degree from accurate. And yeah, Kershaw, the 9 connections as well, Fibonacci, Lucas. Links in the description. Cheers and have a good one.
Okay, let's look at that a little bit further. So the geometric connections of the pyramids, and we'll just look at Menkaura and how the 5-to-8 Fibonacci ratio there also gives a very, very, very good approximate of the nonagon. A bit proud of that one because I think I could not find that same method anywhere else, and it appears to be at least as accurate as the best other methods, maybe the best. But Menkaura Pyramid, and it's also a key to linking the other pyramid. Now, we touched on that earlier. So for instance, the Lucas and the Fibonacci numbers started to give these connections between not just the Giza pyramids but the others as well, so in proportion, but also the way that they relate to one another in size and height. For instance, both the Great Pyramid and the Maidum Pyramid are 7-to-11 ratio, but which are Lucas numbers, so 7 and 11. But the ratio between them, so whether by base or by height, they have a ratio of 1.6 or 8-to-5, 5-to-8, depending on which way you work it. Now that 5-to-8 ratio is the base to height ratio. So, sorry, height is 5 and the base is 8 of a Menkaura pyramid, so divide that by 5. It's 8-to-5 ratio. If you simplify that down, you get 8 is the base and 5 is the height. And both the bent and the red pyramid have the same height as the base of the Menkaura pyramid, and therefore it is 8-to-5, so their relative heights have to be 5-to-8, 5-to-8. It's also, Strabo talks about this, the Cinderella story of the princess with the missing shoe, and then the king, or the princess, where he went out looking for the missing shoe, which lady's foot would fit it, and that's the Cinderella story, comes from the connection to the Menkaura pyramid. But it's all about compass and straight edge and the drawing. So we drew that nonagon from the 5-to-8. Now when it comes to compass and straight edge geometry, so drawing your regular polygons, so equilateral triangle, square, pentagon, hexagon, 7-sided or heptagon, octagon 8, nonagon 9, decagon 10, and undecagon the 11-sided. Where there is matter, there is geometry, and so just, you can examine it, use a different method, but the 360 degrees works just as good, if not better. And so you see now what these numbers represent is the hard angle. So from the center of a triangle, if I was to draw out the lines, each angle, so essentially it's 360 degrees divided by the number of sides. So again, the 90-degree chord would be the inside, or the heart, the angle. 72 degrees would be the pentagon, the hexagon, etc. But you'll notice that the heptagon, or the seven-sided, does not divide equally into 360. Neither does the undecagon, or the 11-sided poly. Geometry is knowledge that appears to be produced by human beings, yet whose meaning is totally independent of them. Now these ones with the green tick are polygons that can be constructed perfectly with compass and straight edge. The knowledge of which geometry aims is the knowledge of the eternal. Now these you cannot. Now think about 120, 90, 72, 45, 36 or 60. All of these you can divide by 3. Now the nonagon, the 9-sided poly, does have an integer, a whole number at its center, the angle at the corner, at the center of it, but you can't divide that by 3. And of course, that these being decimals or fractions, you can't divide them by 3 either. But the nonagon cannot be constructed perfectly with compass and straight edge, but it does have a whole number, an integer, as the angles. Heptagon and decagon cannot be drawn by compass and straight edge, but even when you divide it up into 360, it doesn't work nice. Now I think there's we mentioned the nonagon from the Menkaura geometry, 5/8. Geometry is art of correct reasoning from incorrectly drawn figures. Now that's a thing. Now mathematically, you can draw a perfect equilateral triangle, hexagon, square, but in reality, your compass is vibrating. So if it just depends how. So if you look down at a really high-powered microscope, you'll see that the line from your pencil is very imprecise. Even if you perfectly line up your compass, or your straight edge, to draw a line, you'll see that the beginning of the line is thinner than the end, because the pencil or the pen will release ink or the lead at different rates. So strictly speaking, you can draw them. In reality, you cannot. Now now back to the compass and straight edge. So the nonagon, you can't draw it, but it is 40 degrees. The heptagon and the undecagon, you can't. Geometry enlightens the intellect and sets one's mind right. So we go back to the Great Pyramid over here, and that's 440 by 280, which is that 7:11 Lucas ratio. You can't criticize geometry, it's never wrong. Yes, now 7:11. And that's a good one. It's when I got back into geometry after starting to study the measurements and the architecture, there is a poetry and an imagination and an inspiration that goes into it. It's not this, once you start drawing, even though you might not be the first to discover something, when you do it and you draw it for yourself, you own it in that sense. But 11 to 7, so 11 wide, 7 high. Now I think that's interesting that the two polys of the 7 and the 11 are those which you cannot draw and don't divide up nicely amongst the 360. You can't draw the nonagon, but it does divide up. Geometry is the most complete science. That was on Hilbert's gravestone. We must know, we will know. So the heptagon, 7-sided, nonagon, 9-sided, and decagon, 11-sided, can't be drawn, but there is the 40 degrees there. Now, the Menkaura Pyramid gave us a very, very, very close, hundredths of a degree accuracy to draw a nonagon. Now, if you added a few little steps there, you could even narrow that down, but that even at that level, your thinnest pencil is too thick to do that type of calculation unless you've got a giant drawing board, like a really giant one. But the slope angle of the Great Pyramid, 51.84, which gives approximates of pi and phi and many other features. It's also a reasonably good approximate of drawing a heptagon. Now it's just a touch over half a degree off. Now again, even on a large piece of paper, half a degree is going to be swallowed up by your pen or your pencil. So it's a very good a simple approximate to draw that Lucas rectangle, draw your pyramid, and then you have a nice approximate there. But the nonagon one, very, very close. Music is geometry and time. So that nonagon, now we see the 40-degree angle. Now, what I think is nice is that the nonagon sits right between the 7 and the 11 on the undrawable. And so the angle, 140 to 220 on the outside. Great Pyramid, 440 by 280. Multiply 220 by 2, I get 440. Multiply 140 by 2, 280. Therefore, the ratio between them is 11 to 7. Just like the Great Pyramid, I think it's very nice that this nonagon, which sits between them, gives us that ratio in there as well. So the way that these pyramids geometrically work together, not just the Giza and then Giza pyramids, but how they relate to the other pyramids and to themselves in proportions of size, I think it's there's no metric for coincidence, but like how many connections do you need? And it's not super. It is compass and straight edge geometry, relatively simple, and these types of questions, these drawing the polygons, are pretty much the first that are going to develop. So 5 to 8, the Menkaura Pyramid, which you can use Fibonacci numbers, which you can use to draw a very, very a nonagon more accurate than what the thickness of your finest drafting pencil will be able to provide. It's nice to note that the Vitruvian man as well. So the circle of Vitruvian man, the center of the compass is set on his navel, and that gives us an 8 to 5 ratio as well. So these are the type of connections that appear everywhere. You'll see that same spiral in, well, all across nature in many ways. Great lecture, Magic of Fibonacci Numbers by Arthur Benjamin. He talks so many features in regards to these numbers that you can examine. You'll find them everywhere. They're even in the Mandelbrot set, other Fibonacci numbers. But you can even see in the Pascal triangle there. So there is a, with Euclid 1, proposition 9 bisecting an angle. So get that 32-degree angle. We could bisect it, then bisect it again to get that 8.0. So that's what we drew just before. So it's hundredths of a degree, 7 hundredths. Actually, no, that's tens, hundreds, 7 thousandths of a degree from mathematical excellence, purity. And I did another good nonagon design earlier based off the Flower of Life. It's better, again, toot my own horn, but it was better than Jura's one. And this one it could be another one out there. Maybe someone has used this idea before, but I could not find it. But I think there's a lot of connections there. Now I'll try to remember to share the link. Geek37 channel, he does a lot of geometry as well. I shared that idea with him of the nonagon and Fibonacci numbers, and then he just went off. He exploded. And he was looking at all sorts of other, using that method to come to some approximates of all sorts of different polygons as well. So that was nice to see. Now, Menkaura, Great Pyramid, Caffrey Pyramid, Red, Bent, Maidum, and all those others down, which share the same proportions. And these are works of architecture, of engineering, maths and geometry are the essence of those of that craft, and why they wouldn't put that in there. Now, especially with a pyramid being, well, it's a pyramid, it's simple, but you can hide in plain sight, as they say, lots of information, something that architects still do by their measurements and proportions, the ideal height of a room to the length. It's quite a thing in regards. So there's a person, I think this is, who's to say what's the best way to examine and explore these things, but if you're not doing it with geometry, it's I think it's you're just missing one of the essence of as far as foundation stones go. This would have to be the cornerstone, or at least one of the most important foundation stones when it comes to this type of study. And you can do it like again with compass and straight edge drawing, just drawing with geometry, just from my own experience, it does stuff, it triggers parts of the mind and encourages you to think with reason and logic, but also there's a art to it. It requires inspiration and imagination too. And then if you're really artistic, you can use those as basic designs and then extend from them. And you'll see many artists, Dali and others, where you can find this type of geometry. Even in Da Vinci, people, sort of spot this, and it's photography and cinematography, but by the way they frame shots. Like a really good photographer does not have the lure of your eye should not be to the center. It's usually off to the side, in a golden number type of ratio. So there are ways to apply it in art, engineering. Of course, math, geometry is just the essence, again, in science as well. So I can only encourage you to look further. There's a bit here, bit to see, and it's just how it joins all these things together. Really simple, beautiful stuff, I think. Geometry is knowledge of the eternally existent. Geometry existed before creation. Learn how to see, realize that everything connects to everything else. All of these past masters were geometricians, and so that's something worth considering. Okay, let's go on to the next part and look at the math. We'll use some spreadsheets to draw Fibonacci and look at the golden number in more detail, especially Fibonacci and Lucas connections. So that's the Fibonacci, the Lucas numbers, how they connect, and some other interesting, simple, elegant geometry which you can use to link essentially all of the grand pyramids as well. Now I was going to do a further look at Fibonacci and Lucas numbers, their connection to the golden ratio, but now since the runtime is at getting over an hour and a half, I'll put that as a separate compilation, and just do a few more drawing exercises and then run a few spreadsheets to sort of debunk a few myths in regards to Fibonacci numbers and phi, because it's true, but there's a connect like that. Only the Fibonacci has them. It's actually in all numbers that grow that way, and there are a few other, I think, worthy points to look at. The rather unique connection between Lucas and Fibonacci numbers, which have this link to the golden number, but that's not exclusive to them. It's in any number series that it grows in the same way. A few more drawing exercises, and some spreadsheets just to you can draw it, but you can analyze it mathematically as well. So hope you enjoyed. Have a good one, and I will do this follow-up part in regards to that. So cheers.